Hello guys, and welcome back to another video. And this video will be looking at question 4, which is a topic about momentum and impulse. This is the November 2024 paper. So here they say two trolleys A and B of masses 1.5 kg and 2 kg respectively are held in a stationary position on a straight horizontal frictionless track with a compressed spring between them. The trolleys are released and the spring takes t seconds to return to its original length. The spring then falls to the ground. Trolley A moves to the left while trolley B moves to the right and then up a frictionless inclined plane, rising to a maximum vertical height of 1.5 meters as shown in the diagram below. And then we have our two diagrams there that are displaying this situation. And then they say ignore the rotational effects of the wheels. 4.1 then says write down the principle of conservation of mechanical energy in weights. And this one, guys, will want us to say, but I'll just open the exam guideline as well for this one. But it says that the total mechanical energy in an isolated system remains constant or is conserved. Okay, I'm just gonna open the exam guideline to show you the definition quickly. So guys, the definition of the conservation, or rather the principle of conservation of mechanical energy is as follows. It says that the total mechanical energy in an isolated system remains constant, or you could say is conserved. Okay, that is that definition there. We have other definitions. Obviously this definition comes or rather it's under the topic of work, energy and power. Okay, you can pause here to look at some of the other definitions that have to do with that topic, but we'll do momentum and impulse in this regard. Okay, now 4.2 says calculate the speed of trolley B at the bottom of the inclined plane. So if we go to our diagram, we will see that here this is our what is it, our trolley. Yes, trolley B, and it's at the bottom. However, from this position it goes up and reaches this point here, and this is the maximum height as it is said on the statement. Okay, so what we need to remember when it comes to this particular situation is that they've told us that our trolleys are moving, or rather let's talk about trolley B since it's what we are concerned about. They are saying here that trolley B moves to the right and then up a frictionless inclined plane. So the part here in frictionless inclined plane, this is where our trolley is moving, right? And there is no friction there. And if there's no friction here, it means that mechanical energy is conserved, right? Because of us not having any friction there. And that means we should use here the principle of conservation of mechanical energy to solve this problem. Well, there are other ways, but I'm gonna use that approach in this case. Okay, we'll answer this question over here. So 4.2, we will use the principle of conservation of mechanical energy, and that is what EMAC before. I normally see EMAC. Okay, let's use, yeah, EMAC before is equal to EMAC after. Okay, and then I'm gonna break this down. Remember, mechanical energy by definition is the sum of gravitational potential energy plus kinetic energy. So this, if I break it down, then will become mgh being my potential energy plus half mv squared. Okay, but this will be my initial, so this is my before. Before, guys, is when my trolley is at the bottom. Okay, here the before part is here when my trolley is at the bottom, and the after part is when my trolley is at the top. Okay, then we say equal to, same thing this side, we have mgh plus half mv squared, but this will be my final velocity when my trolley reaches the top. And what you will notice is that, guys, if my trolley is at the bottom, it means that I don't have any height, right? And if I don't have any height, it means if I were to substitute here, my height would be 0, and 0 multiplied by mg would give me what? Would give me 0. So all of this here is going to be 0, right? Then we come to this side. This side is gonna be half my mass. The mass of block B, as you can see, is 2 kg. And then the VI is what I'm actually looking for. I'm looking for the initial velocity because that's when I am starting to have my block move, right, from this position up to there at the top. Okay, then I go to the other side. On the other side now, I do have potential energy since there is this height. That means I'm gonna take the mass of the block, which is 2, and then G is what? 9,8. The height in this case is this 1,5, plus what about half mv squared final. Here, guys, it means that when my block, or rather trolley, reaches this part, the top, the final velocity becomes 0. And if the final velocity becomes 0 here, it means that that velocity will multiply this half m, and everything here then will be equal to what? It will be equal to 0. Okay, so here I will have 0. And when I proceed now, I'm just using my calculator. If you realize, half times 2 should give me 1. So here I should have VI squared. That remains. And then I will see 2. Oh, excuse this. Let me just move it, guys. Yeah. So what I'm going to say is, I'm now going to put this on the calculator as it is. I'll say 2 multiplied by 9,8 multiplied by 1,5, and the value I get is 29,4. And then because I'm solving for the v and it's squared, I'm just gonna square both sides to remove this exponent of 2, and I will have v is equal to, if I put this under a square root, let's see what do I get. Answer I get is going to be equal to 5,42 meters per second. And we'll see here to the right, yeah, it's gonna move to the right, and that's how we'll answer 4.2. okay, for 4.3, guys, I'm gonna remove this part, so yeah, bear with me on that so that I can have space. Okay, for 4.3.1, well, 4.3, they say, for the t seconds that the spring takes to return to its natural position, calculate the change in momentum of trolley B. So, guys, we have to remember that this spring fell off, right? They said that it fell. Remember here they said that the spring falls to the ground, but the question they are asking here is before the spring actually falls to the ground. Okay, and you will see here that they say the trolleys are released and the spring takes t seconds to return to its natural length, and then the spring falls to the ground. So before the spring fell to the ground, it means that our trolleys were still attached to the spring. So we are being asked to find the change in momentum of the trolley. And what you will realize is that, guys, initially the two thingings here, the two trolleys were attached, like in this situation here, that part there, the two were attached here, right? And then they moved to different directions. So initially here they were at rest, if you recall. So that means the velocity of the two springs, the initial velocity of the two springs was what? It was 0 meters per second. And then the springs were released, right? And when the springs were released, we see that this one had an initial velocity of what? Remember, I just want to talk about this from this point to that point. The initial velocity was the one we found, which was 4,42, right? That was the initial velocity here. But this initial velocity, guys, before being the initial velocity, it was the final velocity of this trolley here, because remember, this trolley moved from this position of rest, and then it got to this point here where it was then able to climb up this incline. So this means that this initial velocity, before becoming the initial velocity that propelled the trolley to move up, was actually the final velocity when the trolley moved from the position of rest to here. I will clear on that, guys. I hope that makes sense. Then if we look at the formula for the change of change in momentum, it's delta p is equal to m in brackets vf minus vi, right? And then we will have to remember that our momentum is actually a vector. That means it has to have direction and magnitude, right? Then the same applies with our velocities. They are vectors, so they also have to have magnitude and direction. And if they are going to have magnitude and direction, guys, this is how we'll solve this. Remember, we are dealing with trolley B. We are dealing with trolley B, and we see that the mass of trolley B is what? 2 kg. So where we see m, we are going to put 2 in brackets. We are going to take our direction to the right as positive, because our trolley B obviously moved to the right while our trolley A moved to the left, right? So right will have to be positive and left is negative. So this means that our final velocity of block B, which is this 5,42 meters per second, will be positive. So I'm just going to put it there, 5,42 meters per second minus the initial velocity. What was the initial velocity of block B before it separated from block A? It was 0, because remember, the trolley started from a position of rest. So here we'll have 0. Then we just put all of this on the calculator, and the answer we should get is what? Well, we'll say 2 multiplied by 5,42, and the value we get is what? 5,42. The value we get is 10,84. Okay, our value, guys, here is gonna be 10,84. This will be in what? Kg meters per second. Okay, that's the answer we are going to get. All right, then we will have our direction here, and our direction will be to the right, since this value is positive. It's 10,84, guys. Excuse the mess. To the right. Then we're done with this one. Now we'll move on to the next one. The next one says write down the change in momentum of trolley A. This is worth 1 mark, and it's worth 1 mark because, guys, the change in momentum of this trolley A will be the same as the change in momentum of trolley B, but it will move in the opposite direction. Okay, remember. Yeah, so do remember, guys, as I was saying, that when you look at your change in momentum for two objects, it will always be the same but go in opposite directions. Okay, so if the change in momentum of trolley B is this value to the right, then the change in momentum of trolley A will be the same value. So we'll say delta P will be equal to 10, 0.84, but in an opposite, or rather in the opposite direction, that is 10,84 kg meters per second. To which direction? To the left. Okay, now we are done with 4.3.2. we move on to 4.4. They say they calculate the speed of trolley A after t seconds. So guys, to answer this question, we are gonna look at this keyword. Okay, what is this thing doing? We are gonna look at this keyword here, after t seconds. Okay, well, the main word I'm looking for is after. Okay, when they say after, that means they want us to find what? The speed, which is the final velocity here, guys. They are looking for VF of trolley A. Okay, they are looking for VF of trolley A. And if you recall, we had said here that the change in momentum of this object is supposed to be, the change in momentum of trolley A is supposed to be 10,84 kg meters per second, right? What does this mean? This means that we can use that formula, delta P is equal to M in brackets VF minus VI, to find what? To find this velocity. Okay, and how are we going to do that, guys? Where we see delta P, we know that's our change in momentum, and its value is this one, 10,84. We are going to substitute by it. 10,84 is equal to, the mass is going to be what? The mass of block, rather trolley A, is 1,5 kg there, as you can see. So we're just gonna put 1,5 there. What about our velocity? Our velocity in this case is what we are looking for, minus what was our initial velocity, guys? The initial velocity was 0. Then from there we solve for VF. We know that VF minus this one will give us VF, so we can just divide by 1,5 on both sides. Therefore our VF will be equal to, let's see, if I see 10,5 divided by 10,84 divided by 1,5, the answer I get is 7,23. So that's going to be my speed, and remember that speed is a scalar, so it doesn't have direction. So this will be my answer, and yeah, that's how you are supposed to answer this question, guys. I hope you benefited from this. But since we were on the topic of momentum, I just want to go to the exam guideline to show you the other definitions that you have to know with regards to the topic of momentum. There we go. You have to know momentum, the definition of momentum. You have to know, okay, that's the definition of momentum. You have to know that we have what we call the principle of conservation of momentum. I'm not seeing it here. Let's just go down and see if we can find it. Oh, we are somewhere else now. I think, yeah, here it is. So that's another important thing, the principle of conservation of linear momentum. There it is. So you need to also look at that, guys. Then you have to know the types of collisions that we have. We have elastic and inelastic, but hopefully when you do the next question, guys, I'll be explaining this. But I was just showing that your exam guideline, guys, breaks down the topics nicely. It also gives you the necessary definitions. Okay, so please do always check out your exam guideline when revising. I'll see you on the next video. Goodbye.